Hello, good morning everyone. I am Ishwar from Triple E branch. Today we are going to learn about potential matrices. What is potential matrix? The potential matrix can also be interpreted in economic terms. Suppose that we receive money at a rate of 1 unit per unit time. Whenever the process is in a particular state y epsilon s, then u of x comma y is the expected total amount of money that we receive, starting in state x epsilon s. This is the general introduction. This is the third of the introductory sections on continuous time Markov chains. So our starting point is a time homogeneous Markov chain x equal to xt is to t epsilon naught 0 comma infinity, defined on an underlying probability space and with discrete state space s comma s. Thus s is countable and small s is the power of set of S. So every subset of S is measurable, as is every function from S is to another measurable space. In addition, S is given the discrete topology so that S can also be thought of as the Borel alpha algebra, sigma algebra. Every function from S to another topological space is contiguous. Counting measure hashtag is the natural measure on S, S. So in the context of the general introduction, integrals over S are simply sums. Also, kernels on S can be thought of as matrices with rows and sums indexed by S. So the left and right kernel operations are generalizations of matrix multiplication. As before, let B denote the collection of bounded functions f from S tends to R with the usual pointwise definitions of addition and scalar multiplication. B is a vector space. The supernorm norm on B is given by f equal to supplement of f of x from x epsilon s, comma f belongs to B. Of course, if S is finite, B is a set of all real valued functions on S, and f equal to max modulus of f of x from x epsilon s for f epsilon b. The time space is 0, infinity t, where as usual t is the Borel sigma algebra on 0, alpha corresponding to the standard Euclidean topology. Lebesgue measure is the natural measure on 0, alpha, t. Explanation. In our first point of view, we studied x in terms of when and how the state changes. To review briefly, let t equal to t epsilon 0, infinity is to xt is not equal to x0. Assuming that x is right continuous, the Markov property of x implies the memoryless property of t, and hence the distribution of t given x0 equal to x is exponential with parameter lambda of x epsilon 0, alpha for each x epsilon s. The assumption of right continuity rules out the pathological possibility that lambda of x equal to alpha, which would mean that x is an instantaneous state, so that p of t equal to 0 modulus of x0 equal to x equal to 1. On the other hand, if lambda of x is not 0, alpha, then x is a stable state. Finally, if lambda of x equal to 0, then x is an absorbing state, so that p of t equal to infinity, x0 equal to x equal to 1. Next we define a sequence of stopping times. First t0 equal to 0 and t1 equal to t. Recursively, if tn is greater than is smaller than infinity, then tn equal infinity of t greater than tn is to x, t is not equal to xtn. Well, if tn equal to infinity, then Tn plus 1 equal to infinity. With m equal to sub n epsilon n is to Tn smaller than infinity, we define Yn equal to xtn if n epsilon n with n greater n is smaller than or equal to m, and Yn equal to ym if n epsilon n with n is greater than m. Assuming that x is regular, which means that Tn tends to infinity as small n tends to infinity with probability 1, ruling out the explosion event of infinitely many transitions in finite time. The structure of X is completely determined by the sequence of stopping times t equal to t0, t1 and so on, and the embedded time and embedded discrete time jump chain y equal to y0, y1 and so on. Analytically, the distribution X is determined by the exponential parameter function lambda and the one-step transition matrix Q of the jump chain. In our second point of view, we studied X in terms of the collection of transition matrices. P equal to Pt is to T epsilon 0 comma alpha, where for T epsilon 0 comma alpha, Pt of x comma y equal to P of xt equal to y minus of x0 equal to x comma y epsilon is 2. The Markov and time homogeneous properties imply the Chapman-Kolmogorov equations Pt equal to Ps plus T for s comma t epsilon 0 comma alpha, and so that P is a semigroup of transition matrices. The semigroup P, along with the initial distribution of x0, completely determines the distribution of x. For a regular Markov chain X, the fundamental integral equation connected the 2 points of view is. This is the equation. Pt of x comma y equal to I of x comma y e power minus lambda of x power t plus integral of lambda of x of e power minus lambda of x of s qpt minus s of x comma y ds x comma y epsilon square, which is obtained by conditioning on t and xt. It then follows that the matrix function t tends to pt is differentiable with the derivative satisfying the Kolmogorov backward equation pt equal to pt dash equal to gpt, where the generator matrix G is given by G of x comma y equal to minus lambda of x I of x comma y plus lambda of x cube of x comma y is x square. If the exponential parameter function lambda is bounded, then the transition semigroup P is uniform, which leads to stronger results. The generator G is bounded operator on B. The backward equation holds as well as the champion forward equation Pt dash equal to Ptg. As operators on B, finally, we can represent the transition matrix as an exponential Pt equal to Etg for T epsilon c 0 comma alpha. In this section, we study the Markov chain X in terms of a family of matrices known as potential matrices. This is the least intuitive of the 3 points of view, but analytically, one of the best approaches. Essentially, the potential matrices transforms of the transition matrices. Here is the basic theory. We assume again that x equal to xt tends to t epsilon 0 comma alpha is a regular Markov chain on S with transition semigroup P equal to Pt tends to T epsilon 0 comma alpha. Our first discussion closely parallels the general theory except for simplification caused by the discrete state space. Now here we study the definitions and properties. Here we go. First property. For alpha epsilon 0 comma alpha, the alpha potential matrix U alpha of x is defined as follows. The special case U equal to U naught is simply the potential matrix of x. For x comma y, epsilon square comma u comma x comma y is the expected amount of time that x spends in y, starting at x. The family of matrices U equal to U alpha is to 10th alpha is epsilon 0 comma alpha is known as the relevant resolvent of x. So the proof is, since t tends to pt of x comma y is continuous, u alpha x comma y makes sense of for x comma y epsilon sense s square. The interpretation of u of x comma y involves an interchange of integrals. So this is the equation, and then the inside integral is the Lebesgue measure of t epsilon 0 comma alpha and tends to xt equal to y. Explanation of first property. It's quite possible that u of x comma y equal to alpha for some x comma y epsilon is 2, and knowing when this is the case is of considerable interest. If f from s tends to r and a is greater than or equal to 0, then giving the right operation in its many forms. So these are the forms, and assuming as always that the sums and integrals make sense. This will be the case in particular if f is non-negative, or as we will now see, if f epsilon b and a is greater than 0. Second property. Here it follows that for a epsilon 0 comma alpha, the right potential operator ua is bounded. Linear operator on b with ua equal to 1a. It also follows that aua is a probability matrix. This matrix has a nice interpretation. And our third property is, if alpha is greater than 0, then alpha ua of x1 is a conditional probability density function of xt given x not equal to x, where t is independent of x and has the exponential distribution on 0 comma infinity with parameter alpha. And here is the proof. So explanation of third property. So AUA is a transition probability matrix just as PT is a transition of probability matrix, but corresponding to the random time t rather than the deterministic time t epsilon 0 comma alpha. The potential matrix can also be interpreted in economic terms. Suppose that we receive money at a rate of 1 unit per unit time whenever the process X is in particular state, Y is epsilon s. Then U of x comma y is the expected total amount of money that we receive starting in state x epsilon s. But money that we receive later is of less value to us now than money that we will receive sooner. Specifically, suppose that one monetary unit at time t epsilon 0 comma alpha has a present value of e minus 80, where e epsilon 0 comma alpha is the inflation factor or discount factor. Then u of x comma y is the total expected discounted amount that we receive starting in x epsilon s. A bit more generally, suppose that f epsilon b and that of f of y is the reward per unit time that we receive when the process is in state y epsilon s. Then UAF of x is the expected or total discounted reward starting in the state x epsilon s. Here's the fourth property. Alpha u alpha tends to I as alpha tends to infinity. Explanation of fourth property. If f from s tends to 0 comma alpha, then giving the left potential operation in its various forms. Here are the forms, and in particular, suppose that a is greater than 0 and that f is a probability density function of x0, then fpt is a probability density function of xt for t epsilon 0 comma alpha, and hence from the last result afua is the probability density factor of xt, where again t is the independent of x and has the exponential distribution on 0 comma alpha with parameter a. The family of potential kernels gives the same information as the family of transition kernels. This is the fifth property. The resolvent u equal to u alpha tends to alpha epsilon 0 comma infinity completely determines the family of transition kernels. P equal to pt tends to t epsilon 0 comma alpha. Although not an intuitive form of a probability viewpoint, the potential matrices are in some ways nicer than the transition matrices because of additional smoothness. In particular, the resolvent UA tends to A in epsilon 0, alpha along with the initial distribution completely determine the finite dimensional distributions of the Markov chain X. The potential matrices commute with the transition matrices and with each other. This is the sixth property. Suppose that alpha beta t epsilon 0 comma alpha, then pt u alpha equal to u alpha pt equal to integral 0 alpha e power minus a is ps plus t ds, and b is u alpha b beta u beta equal to u beta u alpha equal to integral 0 alpha 0 infinity e power minus e power minus beta s plus t ds dt. Here is the proof. Explanation of sixth property. The equations above are matrix equations and so hold pointwise. The same identities hold for the right operators on space B under the additional restriction that A is greater than 0 and B is greater than 0. The fundamental equation that relates the potential kernels known as the resolvent equation. Here is the seventh property. If alpha comma beta is on 0 comma alpha with alpha is smaller than or equal to beta, then u alpha equal to u beta plus beta minus alpha u beta is the proof. And the equation above is the matrix equation and so holds pointwise. The same identity holds for the right potential operators on the space B under the additional restriction that A is greater than 0. And next we have is connections with the generator. Once again assume that x equal to xt tends to t epsilon 0 comma alpha is a regular Markov chain on S with transition semigroup p equal to pt tends to t epsilon 0 comma alpha infinite semicell group G. Resolvent u equal to ua tends to a epsilon 0 comma alpha exponential parameter function lambda and one step transition matrix Q for the jump chain. There are fundamental connections between the potential ua and the generator matrix G, and hence between ua and the function lambda and the Q matrix and the matrix Q. Here is the eighth property. Suppose that lambda is bounded and alpha epsilon 0 comma alpha infinity, then as operators on B and hence also has matrices. Here is the proof. Since lambda is bounded, G is a bounded operator on B. The proof of A then proceeds as before. For B, we know from the forward and backward equations that GPT equal to PTG for T epsilon 0 comma alpha, and hence GU alpha equal to U alpha G for alpha epsilon 0 comma infinity. Explanation of eighth property. As matrices, the equation in A holds with more generality than the equation in B, much as the Kolmogorov backward equations holds with more generality than the forward equation. Note that this is the equation. If lambda is unbounded, it's not clear that the second sum is finite. And there is ninth property. Suppose that lambda is bounded and alpha epsilon 0 comma alpha, then as operators on B, A u alpha equal to alpha I minus g power minus 1, g equal to alpha I minus u alpha power minus 1. So this is the proof. This follows immediately from the previous result, since u alpha of I alpha I minus g equal to I and I alpha I minus g of u alpha equal to I. This follows from A u alpha I minus g equal to u alpha power minus 1. So g equal to alpha I minus u alpha minus 1 power minus 1. So the potential operator UA and the generator G have a simple, elegant inverse relationship. Of course, these results hold in particular if S is infinite. So that all of the various matrices really are matrices in the elementary sense. Then there is a two-stage chain. Let x equal to xt tends to t epsilon 0 comma alpha by the Markov chain on set of states is equal to 0 comma 1 with the transition rate a epsilon 0 comma alpha from 0 to 1 and transition rate b epsilon 0 comma infinity from 1 to 0 to avoid the trivial case with both states observing, we will assume that a plus b is greater than 0. The first two results below are a review from the previous two sections. The generator matrix G is G equal to minus A, B, minus B. The transition matrix at time t epsilon 0 comma alpha is Pt equal to 1 by A plus B of BA minus 1 by A plus B per E minus e power minus A plus B of t minus A, B minus B, where t epsilon 0 comma infinity. So this is the end of the potential matrices. Thank you.